All right, if I could focus on math for just like a half an hour, that would be great. Today we want, last time we looked at a sphere of radius 5. Now, the reason that the sphere of radius 5 worked out so great in spherical coordinates is because the coordinates match the thing we're trying to describe. We're trying to describe a round thing, and round coordinates are going to work best. So if you recall, in spherical coordinates, our triple integral I just wanted the volume of the sphere, so it was just 1. We still had to have a rho squared times the sine of phi. That's part of the dv. D rho, d theta, d phi. We just had rho go from 0 to 5. Theta go all the way around from 0 to 2 pi. And phi from top to bottom would go from 0 to pi. So because our coordinates are spheres, the graph paper that we're drawing this on is just a bunch of spheres centered at the origin. Our integral, the sphere itself, is just going to be a bunch of intervals. So the coordinates match the shape, so our description is just a bunch of intervals. So our description worked out to just 3 intervals. So for example, if in rectangular coordinates, I wanted to describe a box, I want to describe a rectangular solid, if I can't spell the letter D, does that mean I can't give the grade D? So if our box is a rectangular solid where x goes from 0 to 2, y goes from 0 to 3, and z goes from 0 to 5, it's really easy to describe this rectangular solid with just 3 intervals because the shape matches the coordinates. The shape matches the coordinates, and so our description is 3 intervals. When your shape matches the coordinates, your description is just going to be a bunch of intervals. So if we want to describe, say, a cylinder with a radius of 5 and a height of 7, the best coordinates would clearly be cylindrical coordinates because the shape will match the coordinates. So your description is just going to be 3 intervals. So let's draw a picture of this cylinder. I didn't specify where this cylinder was, so let's put it in the most convenient location. Let's put the center of the base of our cylinder on the XY plane. And let's put the center of our cylinder along the positive Z-axis. We could put this anywhere, but since we could put this anywhere, let's choose a location most convenient to us. Just like when we're doing the fundamental theorem of calculus, there's that plus C, the constant of integration. Since we can choose any constant of integration, let's choose the one that's most convenient to us, usually 0. So if I want to describe this cylinder, I know I wrote it on rectangular coordinates because that's how we picture things most often. The shape is going to match the coordinates. So if it's a cylinder, the shape will match cylindrical coordinates best. So the description will be in cylindrical coordinates will be 3 integrals. All we have to remember is that in cylindrical coordinates, we need that factor of r to turn dv into volume. Let's say we just want the volume. We need a factor of r because cylindrical coordinates, it's 3 intervals, so the order we write these isn't going to make a difference. R, it goes from the center out to the far point of the cylinder, so R will go from 0 to 5. Theta, we want to go all the way around the circle, so from 0 to 2 pi. And Z will go from the bottom of the cylinder to the top of the cylinder, so from 0 to 7. And because these are just intervals, the order, we can change the order as much as we want. We did write this in cylindrical coordinates, so we have to have that factor of r in our integration. If we were going to use rectangular coordinates to describe this round thing, I don't know, maybe because we like a challenge. If we wanted to use rectangular coordinates, I would have to look at this circle and say the circle is x squared plus y squared equals 5 squared. Now, when it comes to describing what x is between and what y is between, it would be more complicated. So in rectangular coordinates, the last one has to be the last integral has to be constant, so let's use dz. That's the same in polar coordinate, in cylindrical coordinates and rectangular coordinates. Z is the same coordinate, height above the xy or r theta plane. But if we look at this circle from the top, if I want to put dy in here next, now dy, and I'm going to have a dx as well. I got to say what's x between and what's y between. We want to describe just this circle. We've got the z part taken care of. If we want to describe this circle, y will go from -5 to 5. And for all those y values, x will go from the bottom of the left circle to the right circle. So the negative square roots of 25 minus y squared. to positive square root of 25 minus y squared. So in this setup, our dv was simpler. It did not have that extra factor of r. Our integration is going to be more complicated because we're using square coordinates for a round thing. So this is, we're only going to get our pi for the roundness, because we know we're going to have a pi because stuff is round. The only way to get pi is to do trigonometric substitution with this square root of 25 minus y squared. Any questions? So that's one of the things that we want to notice. We were describing some round thing. When we're describing volumes of round things, we know that pi will typically show up. Here's some roundness. Shows up in our integral. But in rectangular coordinates, these are all square coordinates. So I'm making all these corners. The way to make round things is to square root of a quadratic. So here is where our roundness will show up. Questions? So that square root of 25 minus y squared, that's describing a circle. When we integrate that, if we think about the mechanics, that's going to be some trigonometric substitution. Trigonometric substitution is going to lead us to some sine inverse and some cosine inverse. Because this is the sine case, we should expect that. Just make a note of that. Integrate to sine and cosine. We integrate with some trigonometric substitution. That makes some sine inverse and some cosine inverse show up. That's where the roundness is going to come from. That's where pi is going to show up. That's how we get the pi that we know is going to be there. Notice that in our cylindrical coordinates, pi is just sitting there in one of the intervals. Here's why I present this problem without actually calculating the problem. First of all, it's not about whether you can remember to do trigonometric substitution. No one's going to ever ask you to do trigonometric substitution again. Maybe you could take this class again. I don't know. I can't guarantee. I shouldn't. There's never always and never in math. That's dangerous to say. Most likely, no one is ever going to ask you to do trigonometric substitution. I guess if you push your kids and to be engineers, and in the future we still teach math in this way, then they're going to have to, and they might ask you. The best thing to do if you don't remember is to say, oh, I'm sorry, kid, you're going to have to struggle with that. And they're like, oh, didn't you have to do this? I'm like, oh, yes, but I'm teaching you a lesson, and you need to learn to struggle. And then they're like, oh, I'm just going to look it up on YouTube or whatever the 2 decades from now version of YouTube is. And you're like, well, good luck with that. You know what I mean? So the point is not that later on you're going to remember how to do trigonometric substitution. The point is what happens in a trigonometric substitution. We're trading our x integral for a theta integral. And we're using trig functions to do it. What happens when we integrate with trig functions? Inverse trig functions show up. Inverse trig functions is where we might get pi and things like that. Pi and round other constants describing roundness. So what we want to see is that we look at these coordinates, and setting up the triple integral to describe this cylinder is not the issue. Recognizing the reason I use this cylinder is that there's some roundness going on, round stuff going on. And we know that when we're finding volume and area and there is roundness going on, there should be a factor of pi somewhere. Here's where the pi shows up, because one of our coordinates is an angle. So we're just going to be plugging in pi. So look at our integral here also. We're going to get some, no trig functions involved because pi just shows up naturally. We're going to end up with a polynomial. Integrating a polynomial, plugging in the endpoints. Nice. Down here, completely messed up. I want you to understand why it's messed up. Because we're describing a round thing with square coordinates. That doesn't fit. I know I've seen that video where like the cylinder goes into the square hole because everything fits in the square hole. That wasn't the point. The point was not get the stuff in the bucket. It was just a poorly designed way to say match the shape, right? It was just a really kind of ineffective way of doing that. The point is noticing that here's where round stuff shows up. Here we're using square coordinates to describe some round stuff. How are we going to get pi? Because it's not going to just show up in our integral. It's going to have to come from the integration part. And we can see that our integration, the first step of integration is pretty easy. It's going to be x, but x goes from negative square root to the positive square root. So we're going to be integrating 2 square roots of 25 minus y squared dy. And that's going to give us some trigonometric substitution. Also, if we go and switch the dx and the dy around, that doesn't help because then x goes from -5 to 5 and y goes from negative square root of 25 minus x squared to positive 25 square root of 25 minus x squared. There's no cheeky way to get out of this except to just change your coordinates. I put that in the category of the third of the 3 great tricks of math. Add 0, multiply by 1, just do another problem. Just straight up do another problem. And that involves changing coordinates. Like, well, I don't like this problem. This problem can F off. I'm going to do this problem instead. That's how math works. I'm stuck. Can I add 0 and fix it? Can I multiply by 1 and fix it? Well, I'll just do a different problem. Any questions? As students, you have that natural instinct anyway. So I'm like, oh, here are the problems that you should do. I'm like, I'll do problem 1, 2, 3, 7, 8, and 9. And you like get to problem 9, and you're like, oh, 9 sucks. I'm going to pretend that I read that wrong. I'm going to do problem 10 instead. And then when you turn the assignment, it's like, oh, you said 9, and I did problem 10. Man, gosh. That has nothing to do with the fact that I knew how to do 10, and I didn't know how to do 9. And I wanted to make sure the correct number of problems were on the assignment. Shucks. Just do a different problem. Sometimes it works, sometimes it doesn't. I don't know if you're familiar, but Captain Kirk did that. On one hand, I guess he should be applauded for his innovation. On the other hand, would it be unreasonable to say he's unfit for command because of that? So here's one of the exercises that we want to do while we're getting used to triple integrals in these different coordinates. Even though we would not want to integrate, find the volume of this cylinder by integrating this triple integral because it's in the wrong coordinates. It's a mismatch of coordinates. It is still useful to practice writing a triple integral of a known shape in alternate coordinates. What would this cylinder look like in spherical coordinates? What would this rectangular solid look like in cylindrical coordinates or spherical coordinates? So we know that rectangular box, cylinder, and sphere are all easy in their given coordinates. What would those shapes look like in described as triple integrals in alternate coordinates? Any questions? How's everybody okay? And is okay. Being meh is kind of where you want to be. This should be a little bit weird. At least a little bit weird to, I don't really have a cap on it, that most a lot weird. Because we're describing things in a very different way. We're describing things, we raise you to describe everything X, Y, and Z. So here, distance here, distance here, distance here. And now we're asking you to use angles. We kind of asked you to use angles already, like your coordinates. We don't use GPS for like the coordinates, but those are two angles, right? There's an angle, there's a theta and a phi. We don't actually use this phi, but there's a theta and a phi. We're already using two angles. But it doesn't look like it because we're so far from the middle. So that's what we want to do. I want to describe a rectangular solid, a cylinder, and a sphere, not just in the best coordinates, but in the worst coordinates, the other two. I want to be able to describe shapes in alternate coordinates. That's good practice for understanding how the coordinates work. I want us to be able to describe shapes using the wrong coordinates. So these are I want you to come up with 6 descriptions, not like right now. This will take longer than that. We want you to come up with these 6 descriptions: a rectangular box in cylindrical and spherical coordinates, a cylinder in rectangular and spherical coordinates, and a sphere in rectangular and cylindrical coordinates. I'm not specifically choosing a particular box, cylinder, or sphere. You can choose where you want the corners to be. You can choose where you want the central axis of your cylinder. You can choose where you want to put the center of the sphere. Whatever is most convenient for you. So you can choose where they are located relative to the origin. Maybe you want your rectangular box to be evenly spaced around X. So like from -2 to 2. Maybe you like to make your life super difficult and you want the box to go from -1 to 4. I mean, that you do you. That sounds radically inconvenient to me, especially because these cylindrical and spherical coordinates have so much to do with a radius distance from the origin. It might be more convenient to make everything evenly spaced about the middle, but if you want to make your life difficult, I applaud such. I mean, you're already making your life difficult. Why not just go all in and have your rectangular box go from x equals -1 to x equals 3? You know what? That's even too easy because that's just 4. You can just move the middle, -1 to pi squared over e. I don't know. Go crazy. You get to choose where where the object sits, but you do have to be faithful to these coordinates. I want you to come up with these 6 weird descriptions. We've used class time to come up with the 3 easy ones because what am I going to do? Make my life difficult? No. I'm going to use them as examples. I'm going to do the easy ones in class and then make you do the awful ones. I mean, the other ones. They're not awful. They're perfectly nice. You can choose the size of the box, cylinder, or sphere. Make that easy on yourself, but be prepared for follow-ups where I say, what if this happened? What would you have to do to your description? Any questions? Comments? Snide remarks? All right. That's our next big thing. I want you to come up with these 6 descriptions. 6 descriptions. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.